Good. This talk is not by me alone. It's with the help. I made this with the help of Wolfgang Caliber and Alexander Kalinko, my colleagues here at DESY, who are in charge of the other XAFS beamline and who are in charge of the future XAFS beamlines at PETRA IV. So before I start, spring has come to Hamburg and the cherries are blooming and well, all over the place. We had very nice weather last time, so it looks very nice. Good. The agenda for today. I want to start with the status quo that we have at PETRA III today, then briefly introduce the PETRA IV projects, all those parameters which are relevant for XAFS spectroscopy. And then I want to continue with the beamlines that we are planning to build at PETRA IV. And yeah, as a bit of an outlook, the talk very briefly about the use of the coherence by using subtypography. And I want to end with a summary. PETRA III. PETRA III is our synchrotron storage ring here at Hamburg. It's operated at 6 GeV electron energy. It's operated in two different modi. It's either the so-called timing mode with 40 bunches stored in the storage ring, or the a more continuous mode with 480 bunches stored in the storage ring. That makes a huge difference in the bunch separation, and especially this timing mode is very special because the bunch separation is very large, and this is used by a huge community of people who are doing timing experiments. This is simply the combination of this relatively small number of bunches with the large circumference of 2,300 meters of the storage ring. Initially, PETRA was built in 1970s as a high energy physics experiment. It was the place where the gluon was first observed, and since 1988, it was used as pre-accelerator for the next larger high energy physics experiment, that was HERA. And at that time, there was already an undulator installed, which had the first harmonic at 14.4 kilo electron volts, because PETRA was operated, I think, 12 or 14 GeV. Since 2007, the high energy physics program stopped, and PETRA was then rebuilt into a third generation storage ring with undulators and all that stuff. It started operation in 2010 with the first 3 undulator beamlines, and since 2013, 15 beamlines were in operation in the only existing hall at that time. And between 2014 and April 2015, 2 additional halls were built, and one of these halls accommodates the 2 XAFS beamlines. So these were the first 2 beamlines which went into operation in 2016. And you see here a photograph of the hall with the experimental hutch of P65, one of the 2 XAFS beamline, and here at the right-hand side, P64. You see some gas cabinets and stuff. So we equipped the beamlines with everything you need for in situ experiments from the very beginning on. And yeah, 65 is a bit boring because it's just a beamline which is optimized for classical XAFS spectroscopy with a relatively large beam. And yeah, that's the only thing you can do there. You can measure XAFS as kind of analytical method. 64 is a bit more interesting because it offers focused and unfocused beam. It has a XAFS and quick XAFS monochromator. It has 2 monochromators and the respective end stations. It has a urine spectrometer for X-ray emission spectroscopy, and since 1 year or so, it also allows pump and probe experiments with a laser. So we share some equipment because, as I said, the largest user community are definitely coming from catalysis, and so we have gas lines, gas cabinets, mass spectrometer, gas dosing system, and capillary reactor for those groups which don't come with their own equipment. Most groups come with their own equipment. I think that's the same everywhere around the world. And we have a sample preparation lab directly adjacent to the Beamlines. So let's start with the a bit more boring beamline. That's P65. That's my beamline. That's for applied XAFS spectroscopy. 65 was built to be the successor of the 3 XAFS beamlines which we had at DORIS. And well, those were bending magnet beamlines. So on average, the beam was a centimeter wide, a millimeter high, and we had a flux of on the order of 10 to the 9 photons, a monochromatic flux, 10 to the 9 photons per second. So that was nice for transmission XAFS. It was also okay for most fluorescence XAFS experiments, but that stopped the moment the DORIS ring was switched off for good in October 2012. And then there was a gap of almost 4 years during which there was no XRay spectroscopy available at DESY. And from June 2016, we started user operation at P65. P65 was built around a water-cooled double crystal monochromator, which we were already using at the bending magnet beamlines at DORIS. So this can't live with very high heat load, especially not with high heat load density or power load density. So we had to minimize the power load on the first crystal of the monochromator, and therefore we are only using a short undulator with only 11 periods. And we are using 2 plane mirrors in front of the monochromator to cut off the higher harmonics before the then pink beam reaches the first crystal. Then we have this water-cooled monochromator, and that's a very nice monochromator. It's very stable. It doesn't make any problems apart from the fact that we need to minimize the heat load. A final slit just in front of the sample, and then the ionization chambers, the usual stuff, and the sample. What's remarkable is the short distance between the monochromator and the sample, and that helps greatly to improve the stability at the beamline. We have a large beam, and this final slit is, well, kind of bathing in the beam. So the beam that hits this first slit is always larger than the slit, so that we don't see any movement of the beam on the sample, and that allows to measure very nice spectra if the samples are good enough up to very high K values. So overall, the working range is 4 kV to 44 kV with 2 crystal pairs, 111 to 311. The beam on average is 1 or 1.5 millimeter horizontal and about 0.5 millimeter in the vertical direction. And we have between 10 to the 11, 10 to the 12 photons per second. 10 to the 12 is around 9 kV around the Kappa edge. And if we go up to 40 kV, it goes down to 10 to the 11 or 8 or 9 times 10 to the 10 photons per second. So the most of the users are coming from Germany. These are mostly the users who do catalysis. This is by far the lion's share of the beam time. This is simply so because they often bring their own equipment, and the further you have to come from, the more difficult this is getting. Then we have EU users and a large user community from India. There's a cooperation between DESY and India. And so that was always a large user community until, well, 2019, including 2019. Then from 2020, these foreign users shrink to almost zero because of the corona restrictions. 65 is one of the most productive beamlines actually at DESY, and in 2020 I counted about 50 peer-reviewed publications in journals from the users. Typical science is, as I said, is catalysis research, and in this case, this example shows the single platinum atoms on cerium dioxide, and the question was where exactly are these platinum atoms sitting? And the users, that was from Florian Maurer from Jan de Groenewald's group, they did the XAFS measurement at 65, but they, apart from that, they did a lot of other stuff, and they did DFT calculations, for instance, came up with different models which they compared, and to which they compared the experimental XAFS spectra to come up with the solution where these platinum atoms are finally sitting. So that's a very typical example. XAFS is used as an analytical tool, like a method that you use in your home laboratory when you do mass spectroscopy or atomic absorption spectroscopy, well, you name it, whatever you want to do. So 64 is a bit more, yeah, as I say, advanced. It's using a 2-meter long undulator. That's what we would call a full undulator here. At PETRA III, it uses a 2-meter undulator. It's equipped with 2 monochromators, a quick scanning XAFS monochromator and the standard high heat load monochromator. Both are liquid nitrogen cooled. And then the mirrors are behind the monochromator, and both of these mirrors can be used as focusing mirrors, so that you can go down to about 100 micron large beam on the sample. It's further equipped with a von Hammer spectrometer that's making use of the high brilliance of the undulator source, and it has more or less the same working range, at least with the high heat load monochromator of 4 to 50 kV. With the XAFS monochromator, it's currently only usable between 5 and 25 kV, because the 311, the XAFS monochromator has both crystal pairs, 111 is a 311 channel cut, but actually the 311, the heat load seems to be too large, so that the simply don't work there. It's has no weak link, so there's no way to tune the second crystal and to compensate the heat load. So the intensity is really small with the 311. It's not working. And the flux at the sample is about factor 20 to 50 higher than what we find at 65, and we have like 10 to the 13 photons per second in a monochromatic beam at 7 kV. It's the user community is very similar. The names are a bit different here, but energy basically includes the catalysis and battery research and all these things. I have absolutely no idea what enabling technologies and key technologies might be in this here in this framework, but certainly there's also a certain share of batteries and things included in this. But overall, the distribution of user groups is pretty similar. It's also very productive. In 2020, it was more than 40 publications per year. And well, in the beginning, in 2017, there were mainly standard XAFS experiments, and then there's a fair share of experiments with the XAFS monochromator and with the spectrometer. As I said, the pump and probe setup was commissioned during the last year, I would say. So it's only slowly coming into user operation, and it will certainly take a certain share of the overall beam time in the years to come. Good, some pictures from 64. This is the standard setup with the ionization chambers here and there. Sample between the 2 ionization chambers. Here is the lambda detector installed, a 2D lambda detector, to measure the diffraction pattern from the samples. And yeah, the in situ cell, sorry, a 100 pixel germanium detector, which is not very popular among the users and among the Beamline scientists, because it's it's a bit tricky to use, let's say. It's actually easier to use a 4-pixel SDD detector and achieve even higher integral count rates with these 4 SDDs than with these meanwhile rather old 100-pixel germanium detector. 64 is also equipped with special gridded ionization chambers, which are fast enough to measure XAFS and also especially the XANEs of the XAFS with up to 50 Hertz. Then, yeah, another example from catalysis. This was also done, I think, in cooperation with Jan de Groenewald's group and with Christian Schröer from DESY. This is a 2D detector behind the sample, and with a relatively large beam, the XAFS or the absorption of the sample is mapped onto this detector, and then measuring at different points of the spectra where there's a contrast between the oxidized and the reduced form, in this case of platinum. One can see how the reduced and oxidized form of the platinum is moving inside this capillary reactor depending on flow rate and heating, etc. So this gives some insight into what's happening in this capillary reactors. This is, I mean, always a discussion whether this is representative for what's happening in a real industrial reactor or if it's not representative. So this experiment was aiming to solve or to contribute to this discussion, at least. Yeah, the high resolution X-ray emission end station, the Van Hammer spectrometer, this is Alexander Kalinko's work. And it's operational since 2018. It was developing in several steps. Meanwhile, the setup can take up to 16 bent crystals, and is working with these 16 bent crystals. There's a large collection of crystals. I must admit, I don't know if from all of them there are 16 available, but all of those are available, so that it's covering really the whole energy range between 4,000 electron volts and up to 25,000 electron volts. Examples, what was measured or what users can measure with this spectrometer, that certainly includes high resolution X-ray emission spectroscopy with all those satellite peaks of the K-alpha and K-beta peaks, and well, the RIG spectra, and then if you have the RIG spectrum, certainly also the HERFT or whatever one likes to call it, XAFS or XANE spectra, which became very popular lately to the work which was also done at ESRF and other places. And last but not least, very nice, nice illuminated with a green laser, the pump and probe end station, which is the work of Maria Naumova and Alexander Kalinko, and some collaborating groups. It's using a laser to excite samples with this optical laser, and then measure the XAFS or XANEs absorption or emissions, also emission spectra of the excited samples, laser excited samples. At the moment, there is they started to fill a separate touch for I guess more powerful laser, and to fulfill all the safety requirements which are necessary for this kind of work. And this is an example of kind of proof of principle experiment, transitioned XAS in of a myoglobin sample which was complexed with CO. And then you see here some differences between the laser off and laser on spectra, the transient spectrum here compared to a spectrum, to the same spectrum which was published in 2011. But certainly took days to measure with really, well, a lot of noise here. You see the quality is much better and the time was much smaller. For sample delivery, there is a liquid jet sample delivery system available to avoid radiation damage, mainly to have fresh samples for the measurement. Yeah, and I think this might be a good stop, because that was the part of about the present. A good place to have questions, if there are any questions.
Thanks, Edmund. Are there any questions from the audience? Now he shared the current status of PETRA III, Beamlines at PETRA III. So he asked any questions.
Kyotaka Sakura speaking.
Okay.
Okay.
Go ahead.
Thank you very much for the nice talk about the PETRA III present status. So I'd like to ask you the last slide. So you show the pump flow method.
Yeah. And
so you use the liquid system. The last picture you showed.
And this and the Sirius storage ring, the ESRF was modified. The electron optics was modified to the ESRF EBS ring. It's all about achieving a smaller and rounder beam by reducing the emittance, mainly the horizontal emittance of the electron beam. And that allows, or that increases the brilliance of the beam, and that allows to achieve a smaller focus and to achieve a much higher degree of coherence than we had at the third generation source, or that we have at the moment, the third generation source PETRA III. So this plans for PETRA changed. The plans for the electron optics for the lattice changed about 1.5 years ago, and the planning started more or less again. We are now at hybrid 6-band achromat cells on a ring based on these hybrid 6-band achromat cells, which have a lot of advantages compared to the design that was discussed before. The other design was a typical DESY design with a highly asymmetric ring. Now we have a more or less symmetric ring, and the main advantage is that many beamlines can remain more or less at the same space where they are today, especially here in the Max von Laue hall. That's the large hall which is accommodating 14 beamlines at the moment, and these two new halls which were built in the PETRA extension project. But since it's no longer possible to accommodate 2 undulators in one straight sections, we need to build another large hall, which is called Hall West at the moment. And this is here in this photograph. This is actually quite expensive because Hamburg is not flat as a pan as many people think it is. Actually, this part here would be completely under the surface. So this is quite expensive endeavor to build this new hall, but it's necessary to accommodate the beamlines. Where we are now, well, in the beginning with the TDR, or we are in the TDR phase. The beamlines are defined, and we have soon have to start to write the technical design report also for the beamlines. Most important, start of the construction work is foreseen for January 2026. That means that's the time when PETRA III is switched off for good. And in January 2028, it's foreseen to start with PETRA IV with the first beamlines, actually. That will be the beamlines which are in the already existing halls and not in this large new hall. The gain that PETRA IV promises is a huge gain in brilliance. We will gain about a factor of 500 at 10,000 electron volts, and about a factor of 1,000 at really hard for really hard X-rays, and at about 80,000. And actually, the brilliance at 100 kV will be higher than the brilliance at 10 kV today. So that's a huge increase, especially for the high energies, at the higher energies. Brilliance and coherent flux, very briefly, because otherwise I will run out of time. The brilliance is proportional to, or let's start with the flux. The flux of an undulator for a given undulator and a given storage ring with a certain stored current is the same. It will not change. So we don't gain much in flux, but we gain in brilliance because the cone of the beam becomes smaller. And the brilliance of the beam is proportional to the coherent flux, or actually the coherent flux is proportional to the brilliance of the beam. So if we increase the brilliance, we automatically also increase the coherent flux. And so that means this total flux will not change much due to the improved emittance. Actually, it will not change at all due to the improved emittance, but we will see an increase in the total flux because we can now use longer undulators, because we don't need to share them between two undulators, or we can't share them between two undulators anymore. So instead of 2-meter devices at PETRA III, there will be about 4-meter devices at PETRA IV. So there's a gain caused by these longer undulators, but the main improvement will be in the brilliance and in the coherence. So all experiments that do not require focusing or coherence will not profit very much. So that's the case for normal XAFS. Normal XAFS will not profit very much. Actually, the question is, will it suffer? Whereas all the methods which can make use of coherence or brilliance will profit a lot, and this includes certainly all the kind of spectroscopy which is done with a small beam. So yeah, this is the PR, the transparency that's created by DESY's PR department. So it's focusing on the focus beam, small samples, analysis of small particles in environmental samples, in catalysis, or here show where the arsenic in plants is. So we can say that all these micro beam or nano beam methods will certainly profit, but the question is what will happen with XAFS spectroscopy. And so let's first have a look on the what happens if we would transfer our existing beamlines to PETRA IV. So what happens to the undulator beam? Well, the answer is quite easy. What happens is the beam becomes rounder and the flux density will increase by several orders of magnitude. To see, I hope you can see, this is the red here means 3 times 10 to the 18 photons, and the flux density that we have today is about 2 times 10 to the 13. In the unfocused beam, about 80 meters away from a 5-meter long undulator, with 200 milliamps stored current in the PETRA IV and 100 milliamps in PETRA III. So this is a huge increase in flux density. That means also in power load, etc., in radiation damage in the samples, but probably we can handle that. This is might be even more impressive if we look at the flux through a pinhole, which is millimeters squared, about 80 meters away from the source, and here compared the situation at PETRA IV with the situation at PETRA III. So that we will gain in flux. This is sure. If we go to the undulators, and that might be nice. This is also visible when we do the ray tracing of the existing beamlines. Here, the uppercase is P64 at PETRA III, and you see the beam is has this elliptical shape. And this is exactly the same beamline. The only thing that was changed is the properties of the electron beam in the undulator, or which goes through the undulator, and you immediately see that this is will give a much smaller focus. This is becomes even better visible if we look on a screen placed at the sample position. So we have this elliptically beam which is about 200 microns wide in case of PETRA III, and we have this round beam. You see, this is a completely different scaling here of the x-axis, which is order of magnitude smaller in case of PETRA IV. So that these things like X-ray emission spectroscopy with the spectrometer, and those methods would certainly gain from the undulator. And yeah, maybe I skipped these questions here because this was very short part, and just continue with what we foresee for the XAFS beamline. And this is, yeah, good. Today we have 2 beamlines. In the future we will have 3 beamlines. This is good. We are planning to have a successor for P65 plus the option to measure quick XAFS, and that's the point where we'll come to the undulator versus wiggler question. We call this applied analytical XAFS and quick XAFS beamline. Then there will be kind of successor for 64, which we like to call X-ray absorption and emission beamline for the time being. And there will be a new beamline, an additional beamline, which is called, this kind of a working title at the moment, material science beamline. This will actually already, the building of that beamline will start within the yeah, I would say the next months. The plan is, if I remember it correctly, that it will have the first experiments in about 2 years, which might be optimistic. We will see. But this will be a beamline P63. There's a free slot at the moment in our hall, and it's foreseen that it starts at least with some experiments already at PETRA III. In the later stage, at least at PETRA IV, it's foreseen that at this beamline there will be a combination of absorption spectroscopy, X-ray diffraction, small angle scattering, PDF, you name it, collected around the sample. So this is a beamline which, other than contrary to all our other beamlines, focuses on a certain type of sample, material science, catalysis research, and not so much on a method. We'll see how that works. Good. Let's start with the apparently most boring beamline, the applied analytical XAFS and QXAFS beamline. Actually, I think it's a beamline which has some, well, it's worth thinking about, because it's the one beamline which suffers most from PETRA IV and from the changed conditions at PETRA IV. So classical X-ray absorption spectroscopy, as I mentioned it several times, is more or less large, for me, is what I understand under this word, is a millimeter-sized, square millimeter-sized beam. Homogeneous and incoherent beam, if somehow possible, a monochromatic flux which is larger than 10 to the 9, preferably 10 to the 11, 10 to the 12 photons per second, with not too much power density or flux density. And obviously the ideal source would be a bending magnet or a short wiggler. Methods, clear classical things, XANES, XAFS, maybe quick XAFS, in situ experiments, catalysis, batteries. Here are some examples of samples which require such a beam to be successful. And well, the first option would be to use a bending magnet. We discussed that already for PETRA III beamlines. The simple matter of fact is that a bending magnet, oh, sorry, I confused this. The option one is to use the undulator like we did at PETRA III. So this is the example which I'm showing here. Sorry for the confusion. This would work if we use a similar undulator like the one we have. In this case, I calculated with 15 periods. We would end up with a maximum flux of the order of 10 to the 12, 10 to the 13 photons per second. So that it's certainly possible to do the same things that we did at 65. So this is an option which we need to keep in mind in case the other options don't work. And the drawback of this is that an undulator is a more or less coherent source. So we see all these artifacts which are caused by the coherence. We see diffraction from slits, etc. This is real, and these are calculations done with Konstantin Clementiev's and Roman Chernikov's XRT code. These are the calculations. These are observations at P10. And another beamline which is optimized for coherence at PETRA III. We also see artifacts even with a short undulator at 65. You see all these stripes here, which are caused by diffraction on the slits of the beamline. And what's happening is the typical XAFS sample is not ideal, doesn't have ideal homogeneity. So if the beam is moving a bit, we are probing the inhomogeneities of the sample and not so much maybe the XAFS, and we get a lot of additional noise. So that's a bad situation, and one would rather use an incoherent source or source with lower degree of coherence to do the XAFS experiment. The second reason why an undulator is a bit problematic is the fact that it's emitting a very narrow spectrum in the undulator peaks. And in order to broaden the spectrum to do XAFS spectroscopy, we use tapering of the undulator. But this is not without problems. You see that there are kind of oscillations when you move in energy, and these are not only intensity oscillations or oscillations of the intensity, changes of the intensity. This would cancel out with on a good beamline with good ionization chambers. We calculate I1 over I0. Actually, there are also spatial intensity fluctuations, and then again you probe the homogeneity of your sample and not so much the XAFS. So this comes with some problems. Wolfgang showed that the spectrum looks much better, much smoother if you don't use the odd harmonics, but the even harmonics. This is shown here for the second harmonic. But still, it's not ideal, and it's not infinitely white, certainly not. But it's possible to use it, as was shown at 64. One can do XAFS experiments with such an undulator. It can be done, but it's not ideal. And it will be worse at PETRA IV due to the smaller emittance. These oscillations become more pronounced. This is the case here for PETRA III, and this here is the case for PETRA IV calculated. These calculations seem to be more or less correct, as we have seen in the previous slide. We see these oscillations in reality, so we can expect that also this is real and that the problem becomes more severe in the future. The second option, as I already mentioned, would be to use a bending magnet, but as a simple matter of fact, there's simply not enough flux. We have the problem that we are too far away from the source to collect enough of the divergence to get enough flux on the sample, especially if we really plan to do XAFS at that beamline. So this is not an option which we seriously discuss. And the third option would then be a wiggler. And I did some ray tracing using the XRT from Konstantin with a 3-pole wiggler with a really moderate K. So it's not a real wiggler, a real hard wiggler. It's somewhere between undulator and a wiggler, kind of undulator, with a K of 7.5, and that would deliver about 10 to the 12 photons in the monochromatic beam at the sample position. But this calculation was done without any filters and without considering that the optics might not be ideal, etc. So this is really the absolute upper limit, and one can expect that a factor of 5 to 10 gets lost somewhere on the way. And also it requires first mirror here at this position, which might or might not be possible. At least it would be very expensive to have that mirror. So it's a problem with collecting enough of the divergence. And so I also calculated it for a bit longer wiggler with 10 poles. Then we come to the region of about 10 to the 14 photons into 0.1% bandwidth. So that means about 10 to the 13 photons in with silicon 111 acceptance. And that means probably in a range where we would have about 10 to the 12 photons on the sample. That requires detailed ray tracing in the future. The power load is always a concern at a 6 GeV machine, but I think these 3 kilowatts from the 10-pole wiggler would be manageable. And there remain the concerns about this undulator behavior. That means this is not such a nice and smooth, will not be such a nice and smooth spectrum. It will be, it will show structures. This was shown, we already feared that this would happen, that we would see structures in the beam when we were planning for PETRA III. That was the reason why we finally decided to use undulators and not a wiggler. And meanwhile, the first beamlines are working, especially Konstantin Klementiev's beamline at MaxLab, the Balder beamline. It's an XAFS beamline, and it's using a wiggler at a 4th generation source, at a 4th generation storage ring, wiggler as source, collimating mirror, monochromator, very similar to what one would build at a wiggler beamline at PETRA IV. And what he sees are these oscillations. These are experimental, just the intensity in I0 over the energy over long range, and you see all these tiny oscillations here. This is also accompanied by spatial oscillations when you do the energy scans. These spikes here, by the way, are monochromator glitches, so this is not caused by the source. This is caused by the monochromator unavoidable glitches. And well, there are things you can do to smoothen this a bit. You can taper the wiggler. You can change the inclination of the electron beam in the wiggler slightly. There are things that have influence on the amplitude of these wiggles, but they are there. They seem to be manageable at max 4. It seems that the spectrum is sufficiently smooth to measure XAFS, but when you don't do anything, you really see differences in the spectra, or a lot of additional noise in the spectra, depending on the quality of the samples. For perfectly homogeneous samples, it's not important at all these oscillations, both in intensity and the spatial oscillations. But for real samples, and especially for bad samples, this becomes important. As you can see, this is a bad powder sample measured under different conditions with more or less smoothing of the wiggler spectrum. And you see that the spectra get worse the higher these amplitudes are. There's a very nice paper which is in the current issue of Journal of Synchrotron Radiation, published by Konstantin and his colleagues. This explains all these things very nicely. And I think one very nice thing about this paper is that they show that they can reproduce all these effects with the ray tracing code. So that's very nice, because it gives us some hope that we can also have realistic ray tracing calculations for our future source. Our main problem is that the storage ring is so large. So we can place our first optics. Well, we certainly have to place it in the storage ring tunnel, which is a problem with the technical groups. They don't like it very much. This is simply caused by the larger circumference. The second problem is we have 6 GeV and not 3 GeV. So all these effects will be more pronounced because we need to use weaker wigglers, which have more undulator-like behavior. And we have a smaller, we have similar emittance or comparable emittance, but at much higher energy. Good. Second beamline, X-ray absorption and emission beamline. That's Alexander Kalinko's beamline. It is more or less the successor of 64, making full use of the improved properties of the PETRA IV beam. The beam will be smaller, and have more intensity, so that's ideal for small samples. Think of diamond anvil cells or this kind of catalyst samples, where you can now really look at single catalyst grains. And that means things like microsubstromography, emission spectroscopy, pump and probe experiments will be done at this beamline. The layout is comparable to what's available now. The main difference is that the XAFS monochromator will not be used at that beamline, but at the first beamline, which I mentioned. And instead, there will be a multilayer monochromator for pink beam in case that more intensity is needed, or that to protect. In case that more intensity is needed. There will be the laser hutch for pump and probe experiments, and an updated spectrometer for high resolution X-ray emission spectroscopy. This is a technical drawing of this updated spectrometer. It will combine a Johann and von Hamos spectrometer in one instrument. The detector will be mounted on this robotic arm. This thing is already here and is tested currently. So this will be a very nice instrument which really makes use of PETRA IV properties. And finally, the third beamline, Material Science Lab beamline. In charge of that at the moment is, at least informally, Wolfgang Caliber. It's funded by the Max Planck Gesellschaft, and it's pushed and driven by two groups, Beatrice Roldan-Coenjas group from the Interface Science Department, Fritz Haber Institute, and then a group of Serena de Beer, inorganic spectroscopy at the Max Planck Institute for Chemical Energy Conversion. So this is a very fancy thing. It will use two undulators and to do diffraction and spectroscopy at exactly the same time on the same spot. So we get the radiation from these two undulators. One undulator produces high energy X-rays for the diffraction, and the other one, well, the X-rays which we need depending on the edge, and this one will be scanned. The one for the spectroscopy to change the energy, and then a lower monochromator is used to bypass the XAFS monochromator for the high energy for the diffraction, and later to reunite the two beams on the sample, and then you can do diffraction and XAFS at exactly the same time on the same spot. You can also do things like small angle scattering here with this radiation, or PDF. This, as I said, is built around the sample, so there will be many sample environments involved. This is a beamline which is optimized for an application. That means mainly catalysis research, all these kind of material science things, and none of the methods, neither the spectroscopy nor the diffraction nor PDF or whatever, will be the ultimate beamline for that method, but in the combination it will be very unique in the world. Good. The possible locations for these beamlines, for the time being, the plan is that the material science and the absorption and emission spectroscopy beamline will remain in this hall where where today 64 and 65 are located, and that the analytical XAFS beamline will move to the new hall. This is because here we can have shorter distance between source and first optical element. Here it would be impossible to use a wiggler or to use a wiggler as a source. So the decision is based on the possible reuse of existing beamline. This is cheaper, obviously, but also technical reasons like space requirements. All the phase 1 beamlines will be the beamlines in the existing halls. That means there will be no standard XAFS for a while until this hall really goes into operation. I wouldn't expect that this also happens in 2028. There might be another year or so necessary to bring that up and running. Good. Very, very briefly, beyond classical XAFS spectroscopy, use of coherence. Yesterday, there was a talk by Professor Takahashi at the SRI conference in one of the sessions. He's one of the people who promoting and using this method at Spring 8. So the idea is that you do the ptychography, and you do it not only at one energy, you do it at several different energies. So you get ptychographic patterns here, and you get these patterns, and you get them at different energies. So you add another dimension to your to your investigation. You get the 3D information about the shape of your sample with added dimension of chemical information in form of the spatially resolved X-ray absorption spectra. So in principle, you can choose any point in this 3D image of your sample and get the XAFS or at least XANE spectrum of that point. This is a method which is requiring a lot of coherence, and this is taken from publication by Hirose et al. In the Journal of Synchrotron Radiation 2020. It limited, so the bold things are highlighted by me, limited for the present synchrotron light source and require highly coherent X-ray. And that means this is really an application for fourth generation storage ring wherever they are in the world. And I think there is some interest in the XAFS and in the catalysis community to use this method, and I'm sure it can be used either at one of our beamlines here with maybe some compromises in the coherence, or at the coherent imaging beamline at PETRA IV. And yeah, the increase to that's the last slide. The increase of coherence is enormous if we compare PETRA IV, especially in the brightness mode, with PETRA III, so it's several hundred times more coherent beam. And that means instead of days, these ptychographic measurements will be possible within hours, maybe even minutes. So that would make it really usable for a broader community and go beyond proof of principle experiments. To summarize, well, today we have two beamlines where XAFS or labeling methods are used, spectroscopical methods are used. P65 for the classical XAFS is an analytical method, and at P64, yeah, we have a basket of advanced spectroscopical methods and experiments. The super bands or short wigglers might be an attractive alternative at rings with smaller circumference and lower energy than PETRA IV. We have to see whether this is an alternative at PETRA IV. For that, we need to do more ray tracing and go deeper into this topic. Methods that need high brilliance will certainly gain from fourth generation sources. This includes micro-XAFS, XAFS tomography. Ptychographic XAFS is a very interesting method which will profit hugely by the increase of the coherence, whereas classical XAFS and QuackXAFS will not profit much, but I hope that they will also not suffer too much. What's really an option is this wiggler, and this is now something that the machine people and the optics group accepted, that a wiggler is necessary for XAFS, or is at least advantageous, very advantageous for XAFS for certain applications. And we are now seriously discussing about placing optical elements in the storage ring and not 40 meters away from the source, as this was the dogma when we were talking about the beamlines at PETRA III. So I hope that there is some movement and that we can build a wiggler beamline at PETRA IV. And with that, I want to thank you for your patience, and yeah, my colleagues at XAFS Beamlines, especially Maria, Wolfgang, and Alexander, who supported me with a lot of material for this talk and who are here in the audience if there are special questions. Konstantin and Roman for their nice XRT code, which I used extensively already, and for the useful hints and tips how to use this code. And yeah, Kiyotaki, Asakura, and Hitoshi Abe, certainly for inviting me for this talk. Thank you.
Thank you, Edmund, for your great talk. Now he will accept questions from the audience. Any questions from the audience?
So, can I ask you?
Okay, go ahead.
Thank you very much, Edmund. So, I'd like Kiyotaka Sakura. So, I'd like to ask about the page 50. You show some oscillation in wiggler emission. That is due to the undulator character is overlapping the wiggler emission.
Yes.
Is it a correct understanding?
Yeah. Yeah. This is simply, yeah, the undulate-like behavior. It's the, I don't know, 120 odds harmonic of the undulator, and those things unfortunately become visible. And well, the further you go out in energy, you see that here, if you have a close look, it becomes more and more wiggler-like.
Yes.
I mean, like any wiggler, when you go to low energy, it behaves like an undulator. And unfortunately, this will be worse with a 6 GeV ring than with a 3 GeV ring, because we need to use a softer wiggler. So we will probably suffer more than the colleagues at Max 4.
Okay. So if you use 1 pole wiggler, no such interference?
Yeah, this is the reason. This is the reason for this 3-pole. This 3-pole is in principle a wavelength shifter, or 1-pole wiggler, with these start and end periods. Then you don't have the interference. Yeah, that's the reason why we are thinking about this. If this is usable or not really depends on where we can place our first optical element. I did these calculations, which I did here with a slit at 35 meters away from the source. If we could move this to like 20 meters or so, it would be nice. It would be ideal. But here at 35 meter and with the collimating mirror at 37 meter, it requires a mirror which is longer than 1 meter. About the optical surface must be longer than 1 meter, and that might already be problematic. I mean, you can use a shorter mirror, and but then you lose flux, and there's not much to lose. Left to lose, I would say. This is better, nicer the situation at Max Lab, for instance, where you have this the smaller ring with a smaller circumference, a smaller radius of the ring, and there the collimating mirror is at 20 meters away from the source. If I could go to 20 meters, all the problems would be solved. But that needs to be discussed with the optics group if there's space enough. The large circumference also means that the angle between the beamlines is smaller, so there's not much space in the lateral direction. So that's an additional problem. It's not just that the optics people simply don't want to do it. There are technical reasons why it's difficult to do it.
Thank you very much.
Okay, next, Professor Masao Kimura will ask a question.
Okay, Edmund, thank you very much for nice talk. My name is Masao Kimura from KEK. I have 2 questions. The first is a small question about the material science beamlines. You show you can measure, you are planning to measure diffraction, spectroscopy at the same time, right?
Yeah.
So, and that means, and during the changing the energy for XAFS, you just wait for X-ray diffraction?
No, I mean, Wolfgang, do you want to answer, because you are more into this? I can answer this, but
yes, perhaps I can answer. I'm Wolfgang Caliber, so I'm right now responsible for this beamline. The plan is that we have really 2 separate undulators, one for diffraction, one for spectroscopy. That the diffraction undulator will give us higher energy X-rays. So by diffraction, people prefer to do experiments like 20, 40, 60 keV. And the second undulator, which we can tune continuously together with a monochromator. And this way we can call, and then we will have a lower monochromator to steer the high energy beam away from the spectroscopy beam. So as Edmund showed in this visualization of the beamline which I created. And this way we can have both energies, so for the XRay spectroscopy and for the diffraction on the sample, and can measure really both at the same time. So while we measure XRs with 10 keV, we measure simultaneously diffraction pattern at 60 keV. It's not optimum because, for example, we cannot measure in transmission mode because an ion chamber usually reduces the opening angle. So we have to work in fluorescence mode, and then the 60 keV photons always give us a background from fluorescence. The fluorescence will also hit the area detector, so we have to use there some energy discrimination in the detector, or if the fluorescence is too strong, even some attenuators for the 10 keV photons.
So you mean the area detector for diffraction do not see the X-ray for spectroscopy, right?
It arrives there, but the modern detectors like the IGA2 allows you to set a window.
Oh, I got it.
So this way, we get the ring from the 10 keV, but with the energy discrimination at 60 keV, set at 60 keV, we ignore the 10 keV photons.
Okay, I got it. Thank you.
That's at least our plan. And
okay,
so this is the reason why we start now to commission all these different things at the new Beamline and also at P64 right now, that we have some kind of head start, that we know what's working, what's not working, where we have to improve.
Okay, thank you. And the second question is a little bit hard and difficult to answer maybe. And you said, you know, short wavelengths can be good for the classical X-ray absorption, right?
Yeah. Yeah.
So you know, there are two types of users. You know, one is preferred to the a kind of classical X-ray absorption, and the other is like a tychography. Or so, how do you determine the policy in your institute?
Well,
basically, you listen to the user, or you decide only by your facility. Yeah, I know it's a tough question. You know, we have the same.
Not at all. I mean, not at all. I mean, the latter would be nice, but for us, no. We had a series of user workshops, and then there was a call for so-called science instrumentation proposals. So users were asked to write down what they would want to do at PETRA IV. And then we flipped through this and tried to assign these science proposals to certain beamlines. And that during that process, or the end result of that process, was a portfolio of about 28 beamlines for different methods, and then all these science proposals were mapped to those beamlines. So the users were heavily involved in this process. And another criterion that was clear from the very beginning was that there are certainly many beamlines. They were called flagship beamlines, those beamlines which really need the coherence and the brilliance of PETRA IV. And but that at the same time, it's also important to support these methods like XAFS, which are well established since 20-30 years, and which were done for many years, but which are still popular and needed by a huge community, and which are kind of bread and butter. I mean, you see that from the number of publications from the beamlines. The XAFS beamlines are in fact the most productive beamlines at PETRA III. So they produce the highest output of papers, or the users produce this output, certainly. Not because XAFS is extremely interesting, but because the application of XAFS on interesting science problems is the reason why it's so popular. So and there was always the feeling that there should be a good mixture of these two kinds of applications of PETRA at PETRA IV, those which are really cutting edge technologically and which really employ the properties of PETRA IV on the one hand, and then those bread and butter or workhorse methods like XAFS, which don't necessarily need PETRA IV. But there actually in Germany there's no alternative to PETRA. We simply don't have DORIS anymore, and also the Anker storage ring in Karlsruhe is no longer in user operation. Those would have been ideal sources for XAFS, but there is a gap between Jerry Zeitler's benchtop XAFS and the XAFS with high brilliance at PETRA IV or whatever, and this needs to be filled because it's a popular and widespreadly used method.
Yeah, I'm sorry to ask such a kind of question, but we are always, you know, wondering what kind of way we should take, you know. So some, and of course, only in one facility is difficult to fit for all users. So we're just thinking, for example, for one country or one area, we have several facilities, and a mixture of the facility, a network of the facility may be a good solution for the all users. I don't know the real reason, which is the best. Okay, thank you very much, and I'm sorry for asking such a question.
No, that was a very welcome question.
Okay, thanks. Any other questions from the audience? Okay, may I ask one question? When we'll decide right source for the P65 beamline, you are thinking super bands, undulator, and wigglers. So it may affect some parameters of the ring. So do you need to decide well prior to the ring construction?
These we don't have the final parameters yet for the source. So everything we are doing now is we assume parameters like beta functions, emittance, etc., which are highly likely. And so we don't know the details yet. It's foreseen that the electron beam lattice will be fixed very soon, and then we can really start in earnest to do the ray tracing for the different options. And then there will certainly be another iteration with the civil construction, etc., and with the optics group. Is there enough space? All these things, but yeah, at the moment we lack the exact parameters. We can only say, okay, it doesn't look completely hopeless to use a short wiggler, a 3-pole wiggler, or wavelength shifter, I would like to call it. But there are details which we need to clarify. And I think we need to do that during this year, certainly during this year.
Oh. Okay, thanks. Any other questions from the audience? If not, thanks, Edmund, for your great talk. And thank you for joining me during data saving time, right?
Thank you very much.
Okay.